Welcome to my today's session. Today I want to solve a problem from past paper, and this is 2022. So this is example number 3, design of steel to BS 5950. And the question reads, a simply supported beam of effective span 8 meters supports and factored loads are shown in the figure below. Assuming the beam is fully laterally restrained, select a suitable universal section. In grade 43, the strength is S275 still to satisfy shear and bending. Ignore the self-weight of the beam. So the question carries 20 marks. As you can see, this is the beam. The beam is loaded with a point load and UDL. So if we can begin from support A, you can see a UDL of 2 kilonewton per meter spanning at 2 meters. And this is the GK. So the GK means it is a dead load. And then you have a point load of 6 kilonewton 2 meters from A. And this is a QK. QK means it is an imposed load. We have again a loading of 8 kilonewton, and this is QK. QK means imposed load, placed at 6 meters from A, from support A. And we also have a UDL of 4 kilonewton per meter, and this is the GK spanning at 2 meters. And of course, we have support B. So it is a simply supported beam. A simply supported beam, it means it is a beam with only 2 supports. And such a beam you can analyze using the 3 equation of equilibrium. So let's see how you can solve such a question. For you to solve this question, you are supposed first to analyze this beam using the 3 equation of equilibrium. So 3 equation of equilibrium, whereby the 3 equations are summation of vertical forces is equal to 0. Summation of all horizontal forces is equal to 0. And the summation of moment about a point is equal to 0. After determining the reaction at A and also reaction at B, then you'll be able to draw the shear force diagram. So you'll be able to draw the shear force diagram. And after drawing the shear force diagram, it will show you where the maximum bending moment is. So from shear force diagram, you will calculate the maximum bending moment. So this maximum bending moment will be the design moment. So this one will be the design moment. And you'll use this maximum bending moment as the design moment to select or to design this beam. So let's see how we can tackle this question. So solution. So the first thing to do is to factor this loading. And how are we going to factor this loading? We know that ultimate limit load, is equal to 1.4 GK plus 1.6 QK. So we'll begin from this point, from point A to point C. We have a UDL. So this UDL is equal to 2 kilonewton. So this 2 is the GK. So GK is 1.4. So you multiply by 1.4. So this one is equal to 2.8 kilonewton per meter. We'll come again to the point load. Point load, this is AB. So we have at C we have a point load, which is equal to 6 kilonewton. So it will be 6 times 1.6. So this one is equal to 6 times 1.6. So this is 9.6 kilonewton. We'll come at point D. At point D, we have a point load, and this point load is 8 kilonewton. So it's 8 times 1.6 because it is a QK. So this one is equal to 8 times 1.6. So this is 12.8 kilonewton. We'll come to DB. So DB, we have a UDL of 2. So this is a UDL. So this is 4 times 1.4. So this one will be 4 times 1.4, 5.6 kilonewton per meter. So having done so, now we have factored this load. So this one factored load. So we can use this factored load to analyze now this beam. So allow me to capture this information on this column. So the strength class, so the PY is equal to 275, like that. So I can rub here. Again, I want to wrap this loading on the beam so that we can have our new loading or the factored loading, like that. So here we have 2.8 kilonewton per meter, and then here at C we have 9.6 kilonewton. Now forget about the QK and the GK because we have already factored. So 9.6 kilonewton. Here we have 12.8 kilonewton, and here we have 5.6 kilonewton per meter, like that. So I want now to analyze this beam using the 3 equation of equilibrium. So I will say that summation of moment at RA is equal to 0. It means if you sum moment in reference to this point, it should give you 0. So I will begin. This reaction A, this is reaction A, and this is reaction B. So this reaction A, the distance is 0. So RA times 0 is 0. So we will come to this RB. So RB in reference to RA is moving in which direction? So as you can see, this RB is moving in anti-clockwise direction. So it's moving like this. You can see the movement of my hand. So this way. So that is anti-clockwise. So it will be minus the distance 2 from A to B. 2 plus 4, 6. 6 plus 2, 8. So minus 8 RB, like that. After RB, we now come to the a loading which is so close to A. So we have a UDL of 2.8 kilonewton. So in which direction is this UDL moving in reference to point A? Is moving in that direction. So this is clockwise plus 2.8. Again, because we want the moment, you will change this 2.8 first to a point load. So you will multiply by the distance. So times 2, like that. And then the moment of a UDL, it acts at the center of the span covered by that UDL. So this is times 2 over 2, like that. So we are done with this UDL. We come to this 9.6. In which direction is this point load moving in reference to point A? So this is clockwise direction. So plus 9.6 times 2. Again, we'll come to this 12.8. In which direction is 12.8 moving in reference to point A? It is moving in clockwise direction, this way. So plus 12.8. And the distance from A to where 12.8 is 2 plus 4. So this is 6, like that. And then you come to this one, again is moving in clockwise direction. So it will be plus 5.6. Again, we need to change this 5.6 to a point load. So you'll take 5.6 and multiply it by the distance covered by this UDL, which is 2, like that. Then, to get the moment or the bending moment for this UDL, we have said that the moment for this UDL, it acts at the center of this of the distance covered by the UDL. So it will be put a small bracket and say 2 over 2, like that. And then you will add the distance from RA to where the UDL begin. So plus 2 plus 4, like that. Then is equal to 0. Now we can simplify this expression and obtain RB. So we have minus 8 RB plus, let's carry out operation for this, plus 2.8 times 2, yes, times 2 because this will cancel with this. So this is 5.6 plus, so this one done. Now you come to this one, 9.6 times 2. So this is 19.2. Done. You come to this one, 12.8 times 6. So this is 76.8. Done. We come to this one. So it will be 2 over 2 is 1. 1 plus 2 is 3. 3 plus 4 is 7. So we'll have 5.6 times 2 times 7. So this is 78 plus 78.4 is equal to 0. After this, you put the like stamp together. So you have 5.6 plus 19.2 plus 76.8 plus 78 39.4. So minus 8 RB plus 180 is equal to 0. So we have minus 8 RB is equal to 180. No, yes, it's equal to minus 180. So we'll divide both sides by minus 8 by minus 8. So this one, it will cross to the other side. So it will change negative sign to positive sign. So which imply RB is equal to uh, is equal to RB is equal to 22.5 kilonewton. Yes, kilonewton. After getting RB, we can now calculate RA. So to calculate RA, you'll say that summation of all vertical forces is equal to 0. So it means if we take RA plus RB, it must be equal to all the total forces, all the downward total forces. So if we begin from 2.8, we'll have 2.8 times 2 plus 9.6 plus 12.8 plus 5.6 times 2. Why am I multiplying the UDL by its distance? Because you need to convert this UDL into a point load. So to convert it, we'll multiply it by the distance covered. For example, 2.8 times 2, 5.6 times 2, like that. So you can say that RA plus RB, which is 22.5, is equal to, you can carry out the operation for this. So this is 2.8 times 2 plus 9.6 plus 12.8 plus 5.6 times 2. So this is 39.2. So we have RA plus 22.5 is equal to 39.2. So to get RA, it will be 39.2 minus 22.5, which imply RA is equal to 39 minus 22.5 is equal to 16.7 kilonewton. So we have already calculated the RA and RB. So we want now to draw the shear force diagram. Now let's now draw the shear force diagram. So we have calculated RA is equal to 16.7 kilonewton. RB is equal to RB is 22.5 kilonewton. So let's now draw the shear force diagram. So to draw the shear force diagram, you will extend this line like that. Like that. and you will draw the baseline. So this is the shear force diagram line, and it is at 0, 0. So we will begin from A. So from A, we have 16.7. So you'll approximate around somewhere there. So say 16.7. So take this value and write it in your calculator. So it will be 16.7. Because you have a UDL, so minus bracket 2.8, change this UDL to a point load, 2.8 times 2 times 2. So you'll get 11.11. So let's say it's here. So 11.1. So you will draw an inclined line like this. And then 11.1 minus 9.6 minus 9.6, you'll get 1.5. You'll get 1.5. So somewhere like there, this is 1.5, 1.5 like that. And then this line will be constant because there is no loading up to the next loading, like that. So you'll take 1.5 minus 12.8. So you'll get negative 11.3. So let's assume 11.3 is here. So this is negative 11.3, like that. And then we'll come to this UDL and say that negative 11.3 minus 5.6 times 2. So this is 22.5. So 22.5 is somewhere like there. So like that. So this is 22.5. And 22.5 minus RB is 0. It brings you back to 0. So as you can see, this one is positive shear force, positive, negative. And then you shade your respective areas. Like that. So after having done so, what we need now to calculate is the maximum bending moment. And the maximum bending moment, so the maximum bending moment will always occur where shear force is 0, or where the shear force changes sign from positive to negative, or vice versa. So our maximum bending moment will be at this point. So this is where our maximum moment will occur. Now we want to calculate the maximum moment at this point, because it is point where the shear force is zero. As you can see, this is a zero line or a zero baseline. So, and it is also where the shear force is changing from positive. So this is positive to negative. So let's now find the maximum moment at this point. So M max is equal to the area. If we can start from the left side, so it will be the area of this. This is a trapezium, and this is a rectangle. So it will be the area of this a half a plus b. So a plus b is is the the two parallel side, which is this one and this one, like that. So it will be a half a plus b. This is 16.7 plus 11.1 plus 11.1 times h. H is this from here to here times 2, like that. Then plus the area of this rectangle, which is length times width. So it will be 4, this 4 from here to here times 1.5. So this one is equal to 16.7 plus 11.1 plus 4 times 1.5. So this one is equal to 33.8 kilonewton meter. You can also do it using this formula. So let's get the moment at x. So let's say this point is x. So this second method, to get the moment at this point x, you can either consider the left side of this x as you move to the left support, which is A, or the right side of this support as you move to support B. So the two cases will give you the same answer. So I want to use the shorter sides. So the shorter side is this right side from X to support B. So I will say Mx is equal to, if I sum all the moments at this point X, I will start with reaction at B. In which direction is reaction at B moving in reference to point X? So it is moving in anti-clockwise direction. So it will be 20 minus 22.5 times the distance is 2. Remember, all the forces moving in anti-clockwise direction, we consider them as negative. And those moving in clockwise direction, we consider them as positive. Then we come to this UDL. So UDL, it starts from here. No, it starts from here and ends here. So from here and it ends here. So it is clockwise direction. So plus 5.6 times 2 times 2 over 2. Then we come to this one. Then you come to this one. So 12.8 times 0, because the distance is 0. So it will be 0. So the answer will be, let's check the answer. So the answer is negative 33. Negative 33.8 kilonewton meter. So you will ignore the negative side and take positive 33.8. So this one is equal to 33.8 kilonewton meter. As you can see, the answer are the same. This one and this one are the same. So this maximum bending moment, this maximum moment, which is 33.8 kilonewton meter, will be used as a design moment. I can now rub here because we are now done with the analysis. Now, initial selection. Initial selection. So for initial selection, we know that the plastic modulus, which is Sx, must be greater than m over p y. So therefore Sx must be greater than m. M is 33.8, which is in kilonewton meter. So you will multiply by 10 raised power 6 all over py, which is 275, which imply Sx is equal to 33.8 times 10 raised power 6 over 275. So this is 122.9 times 10 raised power 3 millimeter cubic. Remember, Sx, which is the plastic modulus, in the table is given in centimeter cubic. So therefore, you will multiply this by 10 raised power negative 3. So Sx 122.9 times 10 raised power 3 times 10 raised power negative 3. So we are changing it from a millimeter cubic to centimeter cubic. So therefore Sx is greater, or should be greater than 122.9 centimeter cubic. So you will go to the table using this value and pick the section size of this steel. So I proceed to the table. Now this is the table, as you can see. So our plastic modulus, which is Sx, we have calculated as 122.9. So we want now to pick a value which is higher than that. So we'll come here to our table. I hope you know how to read the table. So you can see here is the plastic modulus. So we'll go for the major axis, which is xx, and we pick a value which is higher than that. So our plastic modulus from the table is 124. And then we will pick the section size. Let's come and pick the section size. So as you can see, the section size is just where my cursor is 153 times 89 times 89 times 16. So 152 times 89 times 16. So you will write the section size. So you will say try 152, this is the depth, times 89, 89 is the width, times 16 kilogram per meter. And the SX from the table is 124 centimeter cubic. And then of course we'll pick other properties. We'll come and pick other properties. For example, you will come and pick, let me show you. So this is our section size we have selected, which is 155, as you can see, times 89 times 16. So you'll come and pick other properties. We have D, 152. You can see where my cursor is, 0.4. We have B, 88.9, T, like that. All of them. You'll pick all of them. I know you know how to read it. So let me write it on the board so that we can continue. So these are the section properties. I'll put them here. So we have the D, which is 152.4. So the section or the properties. So D is 152.4, B is 88.9, T is 4.6, T, small t is 4.6, capital T is 7.7 millimeter, D over T is 26.5 millimeter, B over T, so this, they don't have units. So IXX is 838 centimeter raised power 4, ZXX is 110 centimeter raised power 3, and then small d is 121.8. Now let's now proceed to what we call strength classification. So strength classification. So strength classification. So for strength classification, we always use capital T. So T is equal to 7.7 millimeter. And from the table given by BS 5950, so T 7.7 millimeter is less than 16 millimeter. Therefore, the strength, therefore Py is equal to 275 Newton per millimeter square. I will show you the table. I'll show you the table. So this is the table for strength classification, but I think you already have the table. You already have this table. So we have less than 16 millimeter is 275 Newton per millimeter square, less than 40, but more than 16, 265, like so, like so. So that is how you classify the strengths. So we now proceed to section classification. You have the section classification. So we'll begin by the flange. So the flange we will use B over T. So B over T is equal to 5.77. So 5.77, if you check in the table, okay, let's get this value for this formula. So this one is equal to 275 over py. So this one is equal to 275 over 275. Then you get the square root, which is equal to 1. So for b over t, which is equal to 5.77, must be less than 9.0 this. So automatically this is 1. So you will say flange is class 1 plastic, because if you substitute this e by 1, it will remain 9. Therefore 5.77 is less than 9, which make this flange to be classified as class 1 plastic. This is the table. You can see it. So b over t 9.010 e 15e and so on. D over t 80 e 100 e 120 e, and then we proceed to the web. So the web, we will use d over t. So d over t, which is equal to 26.5, and this one is less than 80 e. So if you substitute this e by 1, it will remain 80. So therefore the web is also class 1 plastic, like that. Then you will say the section which is 152, by 89 by 16 is class 1 plastic, like that. Then after that, we now proceed to what we call the shear strength. So we now proceed to the shear strength. So for shear strength, we'll first check if shear buckling will be considered or not. And here we will use d over t, which is equal to 26.5, and it must be less than 70 e. So our e is 1. So therefore, no buckling, shear buckling will not be considered. So therefore, shear buckling will not be considered. Like that. So our FV, so from the analysis of the beam, we calculated RA, and our RA was 17.6 kilonewton and RB is 22.5 kilonewton. So we will use the maximum reaction. So we will use the maximum reaction as FV. So here FV is 22.5 kilonewton. So we know that FV must be less than PV, which is shear capacity, for the section to be okay. And PV is equal to 0.6 py dt, like that. So this one is equal to 0.6 times 275 times d. D is 152.4, times small t is 4.6, of course, times 10 raised to power negative 3, to change or to get our answer in kilonewton. Yes, in kilonewton. So the shear capacity, which is PV is equal to 116 kilonewton. So as you can see, FV, which is 22.5 kilonewton, is less than PV, which is 116 kilonewton. Therefore, okay. Now what follows next is to check whether it is a low shear load or a high shear load. So let's see. So check if it is a high or low shear load. And for a low shear load, FV is less than 0.6 PV. So this is a low shear load. And then for a high shear load, FV is greater than 0.6 PV but less than PV. So this is a high shear load. So now we need to find 0.6 PV. So 0.6 PV is equal to 0.6 times PV, which is 116. So this one is equal to 116 times 0.6. So this is 69.6. And our FV is 22.2. It therefore means FV, which is 22.5, is less than 0.6 PV, which is 69.6. Therefore, it is a low shear load. Therefore, low shear load, like that. Now, for a low shear load, we will now calculate the moment capacity. So this moment capacity is for a low shear load. So moment capacity is given by this formula. Moment capacity is equal to Pys, and it must be less than or equal to 1.2 Pyz. So let's check. So Py is 275 times S. S is 124. This is from the table. 124. 124. And then remember, this is in 124 is centimeter cubic. So we want to change into millimeter cubic. So times 10 raised power 3, like that. And then, because our answer will be in Newton millimeter, and we want our answer to be in kilonewton millimeter, in kilonewton meter, so you will again multiply by 10 raised power negative 6, and it must be less than 1.2. Py is 275 times Z. Z is 110. 110 you'll multiply by 10 to power of 3 to change it from centimeter cubic to millimeter cubic, like that. So let's see. Let's carry out the operation. So again, remember to multiply by 10 to power of negative 6 so that we can have our answer in kilonewton meter. So this is 34.1, and it is less than, if you carry out the operation, you will get to be 36.3 kilonewton meter. Therefore, okay, like that. Therefore, okay. So remember from the question, if you can follow instruction, we were told that to ignore the self weight of the beam. So it means we will not calculate the moment due to own weight of the beam. Therefore, we'll just compare the moment capacity to the applied moment. So the applied moment which is 33.8 is less than the moment capacity, which is 34.1 kilonewton per meter. Therefore, okay. Therefore, section is okay. And that marks the end of this question. So, for those who have not subscribed to the channel, subscribe and hit the notification bell so that you may be the first person to be notified when I upload a video. So, thank you for your time.